Hi everyone, good morning.
Good morning, Shrikant.
Good morning, sir.
Okay, so meanwhile, I pull up the slides. Anybody has any questions?
Yeah, Shrikant, I have a few
Yep,
questions here.
go ahead.
So, like yesterday, you were telling how to import a library. Like if you want to import, you can like from SciPy import stats, and you don't need to import the whole of the library. Just import a
Right,
small module after that.
right,
Now
right.
there is another way that is mentioned: import matplotlib dot pyplot as PLT. So that is also same way of doing the same thing, correct?
Yes, yes. So inside the matplotlib, under that pyplot module, that
Mhm.
module I'm importing, but I'm naming it as small name as PLT.
I
Just
got
like NumPy
so,
को हम NP बोलते हैं, the same way. Yeah,
so it's the same thing. We are just importing
yeah,
a module in both of them. And in
right,
second, we are also naming it, but there's no other difference. Yeah?
right. No other difference.
Okay. And in that yesterday, like we were doing that box plot, I couldn't understand what is this notch over there, notch true or notch none. I think none was there. Yeah, I think by default. So I didn't understand what is that, what is the purpose of that notch in the box plot?
So have you tried putting it as true or false? Just try that, okay? It would be just, I think, on the visual side. Even I'm not sure, so I need to check on that. So we can get back to you.
Okay,
So
okay, and
just you,
yeah,
if you
okay,
want to know, what any that argument, the
yeah, I
purpose.
tried that actually. I could not find the difference. So that's why I was asking. Anyway, so I'll try
Okay.
once again.
Yeah,
And there was another one, data frame dot describe. Now here we can use include all means all columns
all
or just
columns,
the
all
numerical.
columns, all
Yeah.
columns.
So there is one that says include object. So what does this mean? Object. When you say object, what does it mean? I mean,
Object in Python means categorical variables. So when you say object, it will only work on the categorical columns. So it will describe you only the categorical columns. So when you don't put anything, then it will pick up only the numerical columns or the continuous columns.
okay. So by default, it is numerical. So
Numeric. Yeah.
So when you said object, I mean, which are those categorical columns? I mean, like there were three columns yesterday.
Yeah.
So when we ran that,
The ordinal, the categorical column was there, right? A, B, C, D. So those are, that particular column has been considered as object. So I'll cover that part. Okay.
okay,
When you say dataframe.info, then it will show you which of the columns have been defined as object and which of the columns has been defined as numeric. Okay. So automatically Python picks up and identifies the data type based on the values a particular column has. Okay. Um, so based on that, it will basically label the data types, whether it is a categorical or in Python language, whether it is an object or whether it is a numeric. So if you are not um comfortable with that kind of labeling or assignment, then you can go and change the data type by using as type function. I hope all this has been covered in the
no,
panel.
as type, yeah, as type, I
Yeah,
understood. Yeah, I got it.
yeah.
But this was little like, I mean, this was data frame had three columns: numerical, categorical, and ordinal. So
Yes.
if you use all, then it will show for all numerical, category, and ordinal. But
Hmm.
we said include object. So then it just talking
Just
about the
work on categorical.
categorical.
Yes.
So that means a non-numerical. It doesn't have numerical in that
Yes, you can,
column.
yeah, you can consider in that way as of now. But later when we pick up other use cases, you'll find that even in the categorical column, there could be numbers. But in those scenarios, you have to go and convert those columns as object. So how it works in Python is where if the Python finds numeric values in the column, then it will automatically picks up as a numeric column, even though you have to use it as a category. For example, there are three categories and you have defined it as 1, 2, and 3. Okay. So, but Python, you have to explicitly say that, okay, this 1, 2, 3, I want to use it as a categories. So then you have to convert the data type to object. Then it will be considered as category. Otherwise,
Okay.
automatically it picks up as numeric.
Okay, fine. I'll probably test it out furthermore.
Right.
Fine.
So by now, you just don't worry. Okay, these things will come again and again and again. Every use case, we have to do all these things. So if few things is not clear, then it will get cleared. Okay, as we will discuss on other use cases. Anything on the concept side, I'm more interested
No,
to know if these concepts are clear for you.
I think concepts are fine. The only thing is when we use these modules or functions, the application side, there are so many options.
This by practice, again, listening and going through it, you will get it. So that's for sure. And in case if you have more questions or more queries, then we can have one dedicated session only to address the Python queries. Okay, so that we can take it, that we can plan.
Okay, fine.
But for
Thank
now,
you.
just don't worry on that programming side too much, because that will be covered again and again, and automatically you will get. So it's all about practicing. Okay, so we will keep practicing every time, and then all those concepts will get clear. Okay. All right. So any other questions, guys? All right. So yesterday we kind of touched upon this topic like sampling. Okay. And we kind of discussed like why sampling is important, right? Um, so can anybody just quickly tell me what is the difference between the population and sample? How you will define it? See, now everybody must be knowing this answer. Now this is an exercise where I want to know that how you will structure the answer, how you will frame the sentence. That is also very important. And this is something I will keep on asking you so that you will get prepared, right, how to answer the questions. This is a major challenge, guys, in data science. We feel that, okay, we know this topic, but when it comes to explanation, sometimes we couldn't able to frame the sentence properly. We find difficulty in terms of answering that particular question. So simple question I have asked, what is the difference between the population and the sample? And why sampling is important? Can someone answer that question?
So when you have a large data set, generally, so in that case, you can't get the data from everything. So sampling means you just pick a random smaller subset of that population and try to get that, the mean, whatever median values, just to have that same data.
Mhm.
So it's easier. I mean, instead of running through a large, very, very huge set, which might be in billions of entries, instead of that, we just choose maybe some random subset and run the same operations and get the values. So we expect them to be closer to the ideal values.
Okay. So any other uh, thoughts?
Yeah, population is kind of a superset wherein we have the entire entities lying over there, and each set of data can have different characteristics. So sampling should represent all the characteristics, which is in a subset of the population, wherein when we superimpose, it could actually end up representing the entire population.
Okay.
Yeah, I'm more taking an example of our election surveys and giving that definition. So,
Right.
yeah, when we take the population can have different characteristics like caste, religion, age, and different sexes, and the rural or urban population. So when we take a sampling of that or a sample size of that, if the percentage population of urban is 25% and the rural population is 75%, when we take a sampling, our sample size should actually represent that so that we can get an actual value. That's
Right. Right. Yeah. So I think you all know, what is the difference. But while framing the sentences or while be more confident. Okay. So what happens is when you are giving the answer to the interviewer, uh, even a very short and crisp 1-2 lines, if you answer, that would be more impressive. Again, I'm giving tips and tricks. So if you are answering and again you are trying to explain that by giving some examples and all those things, uh, I think you would also agree. Sometimes interviewer feel that okay, he's also not sure. That's the reason he's trying to give the examples to explain it properly. Okay. Until otherwise, you just give a short and crisp to the point answer. Okay, that is all required. If he interviewer asks you to okay, explain me further, I didn't get it, or give me some example. Okay, so where the sampling would be required, or where you use samples, there you can go ahead and give the examples. So population is something, okay, if let's suppose you have to do the analysis, and for that analysis, you have to capture or you have to consider every entity or every unit. So if you consider every unit of that, then it becomes a entire population. And the first thing what you have to mention is to collect that kind of a data could be impossible or could be difficult and could be time consuming and may cost you, uh, it could be of high cost. So for that reason, we go with the sampling, where we just take the subset of that population, which represent the entire population, and we do the analysis on that sample so that we can infer about the population. So I've given you, but don't take exact the same, but you try to, that's the reason I'm saying, you always keep the book and pen beside you and take the notes. And for every each of these topics, put your thoughts and write 1 or 2 sentences in your language. In that way, you will remember. So do not buy hard, do not mug anything. Okay, just put your thoughts and very nicely in a very good English. Okay, just describe that particular point. Okay, so if in one question, if you keep on explaining it for 2 to 5 minutes, roughly it doesn't give the good impression, okay, on the interviewer. All right, so okay, so now we will proceed. All right, so let's suppose in a population, if you have, as you mentioned, you may have to deal with different characteristics of that entity. Okay. And in the sample again, you have to make sure that all those characters, all those different uh, types of units needs to be captured. So if it's like machine, so there could be different models of machines. So you have to make sure that at least one machine from each model should be present in your sample. If your data in the sample get biased towards any one type of model machines, then your entire analysis will be more biased towards that type. But you don't want that, right? So it is always better while taking the sample, there should not be any biasness. It has to be a very clear representation which you need to see in your sample as population. Okay. Now, okay, so what are the different kinds of sampling? First is the random sampling. Okay. In random sampling, this is also called as probabilistic sampling. Okay. And the second is known as non-random sampling. Now, this non-random sampling is non-probabilistic, and you follow some technique, to derive sample. So some methods or some techniques you will use to to create these kind of samples. Now let's discuss about the random sampling. See, as I mentioned, your sample should not be biased towards any one kind, okay, or any one type. So for that, you generally, what we do, okay, when we play a game or we want to fare, we just go blindfolded, right? Somebody closes your eyes and then you pick something, okay, and then we say that it's a fair decision. So here also random sampling is something like that, okay? So randomly, without having any bias or without having any knowledge about the data, you pick up the observations. It's just like in the box, you have a lot of different kinds of balls inside the box, and it is completely packed. You don't know, what color of balls you may choose when you pick up the ball. And every time, you are picking up the ball and placing it back. Okay. So why placing it back? Then in that case, every ball will have a equal probability. So if you have a 10 balls, picking up any ball, one ball, from that box would be 1 by 10th. The probability would be 1 by 10. If you pick one ball and put it aside, then picking of another ball would be what? Would be 1 by 9, right? So every time if you're picking the ball and putting outside, the probability of picking any ball would increase. So in that case, what we do is uh, it is called as probability with replacement. So you pick up the ball, mark it that I have picked red ball, and again put that red ball back to the box. So in that case, picking every object, okay, from a box would be having a same probability. Now that is known as random sampling. In the random sampling, just imagine, okay, the box is nothing but your data frame and the observations are nothing but your objects. So in the data frame, from the data frame, you just randomly pick the observations. So whatever observation comes, okay, that is randomly picked. So nobody will question you, and there is no biasness in that. Okay, it's randomly picked, okay, based on the probability. So and whatever number of observations you will decide, that many number of observations you pick it up randomly, and that would be your sample. So so in the real scenario, what happens is in the data warehouse or in the data lake, there could be millions of records, as you mentioned, million and billions of records. Now, first thing you have to decide is all this data or all the observations are coming out from the same environment. You remember the environment we discussed, right? So are these observations are from the same environment? See, whenever you are picking up the observations, all the observations which you're randomly picking should follow a similar characteristics. Then it makes sense, right? If they are from different environment, then again, what will happen is, for example, there are two different environments. I'll take an example of vehicles. Guys, please go on mute. Or do you have any question? Okay. So let's suppose there are two different environment. I took the example last time of the tractors, right? The tractors moving in the fields, tractors running in the construction site. Okay, so these are the two different environments. Let's suppose in your database, you have more scenarios of uh, construction sites, okay, vehicles. Now, if you randomly pick the observations, there could be a high chance that based on the probability that more observations may pick up, from the construction site, right? And it could may happen that all the observations might pick up from the construction site because 80% of the data are from construction site. So now that minor category, okay, which is the tractors which are running in the fields, so you will have no observations related to that particular environment. So all your analysis may go wrong, and even when you're training the model, your model will be get biased to only this kind of environment. So for that, we will talk about stratified sampling. What it does is it will create two different groups of data, okay, related to the environment. And from each of the environment, based on the proportion, it will pick up the observations. But again, picking up the observations would be random sample. So two ways. If the observations, all the observations are similar, okay, and the environment is the same for all the observations, you randomly pick the observations from that particular data, and that would become your sample. If it is like they are different environments, then you have to go with stratified sampling, which we will discuss, where you have to create a strata. Strata is nothing but the group. And that group you can create based on the environment or based on the characteristics, whatever, business logic you have to apply. And from each strata, you can pick up randomly certain points. So you have took the example of the elections, right? So now in the sample, I want people from every age group. So age could be one criteria of creating the stratas. Then second, uh, caste, religion, then region. So all these could be categories or the stratas from which you can randomly pick certain uh, certain people or certain observations, and then you can do your analysis. So in that case, your sample would be a clear representation of your population. Okay. So in this, the major important thing is like it eliminates bias. In data science, bias is something you always need to minimize. Okay. And the bias can come in multiple ways. It may come through data, it may come through manual intervention. Um, so they could be different, or it could be because of the algorithms also sometimes. Okay, so you have to always validate that there is minimum bias, okay, in my analysis. If they are biased, then you have to find a way to reduce that biasness. So now first bias may come because of sampling. If you are generating the samples manually, manually in the sense you are using some techniques or some judgment while picking up the observations, you are inducing bias in your data. Okay, so I'll give you an example. For example, now you have to do some analysis on kids. How you will start? Okay, you will not consider urban, rural, nothing. Okay, you will just look out for kids around you. That is known as convenience sampling. So you will just look at the kids around you in your society, in your circle, and then you will do the some kind of analysis on top of it. So is it a clear representation of the population? Of course not, right? You have just considered the kids who are around you. Probably that may not represent every kid, okay, which I want to analyze in my population. I have skipped urban population. I've uh, skipped, the kids with in urban location with below poverty lines, the kids in rural areas. So I have not considered the right sample. So in that case, the biasness get induced in my selection process, in my sample. Okay, so that's the reason it's always better to go with the probability. And for probability also, okay, now you have the same use case. Now, how you will use random sampling here, right? So for that, you need to create some kind of a database. You have to first get that database. You have to find out how many kids are there, okay, in rural, urban, some kind of, details you require for that. And then you can randomly start picking those people, and randomly you can reach out to those people and then start doing your analysis on top of it. So in the malls also, okay. So randomly people are get picked. It's not, they don't use any bias. Probably, as it is a manual process, when the guy, who is taking the survey, probably by he may use some kind of thought process in terms of picking people, right? So there also some level of biasness is there. If it is like a kind of a machine, or if it is like completely open survey, then some level of biasness can be reduced. Okay, so then comes the non-random. Here, it's a it will not have any probability. It's non-probabilistic way of sampling. And here it will open up the some level of selection bias. And when there is bias in the data, then that data generally we don't consider as appropriate for some statistical analysis. Okay. Now, when it comes to random sampling techniques, there are different kinds of random sampling. One is simple random sampling. Simple random sampling is nothing but I have a complete data. As I mentioned, all the observations are sitting in this particular data. It could be a data warehouse, it could be a data lake, it could be any big uh, table, okay, from where we have to pick up some sample observations. So from here, we will just try random sampling, and based on the probability, we'll pick up the observations. Now, these few observations would be my sample. Okay, so now the simple random sampling technique we use for machine learning. And entire all the statistical analysis and even the machine learning model development, everything works on samples. Okay. Now, because the statistics is such a powerful, I would say, subject, uh, with just a smaller data set, it can able to generate a lot of meaningful insights. So even the machine learning algorithms, you give just small set of data, it will able to learn all the patterns if the sample is good. So it's like a an intelligent student. You need not to give every damn book to that person, to go and read and understand the concepts. You just give few books, good books, and he will read it and he will get the concept. And now you give any question from any book, that person will able to answer. So even the machine learning algorithms are like that. And as a data scientist, we need to develop that kind of a model which can learn from a smaller data set and can able to generalize well and can able to provide accurate results. So simple random sampling is a sampling technique where every observation from the population will have a equal probability to get picked. Okay, and you can define whatever number of observations you need from that particular population, and that will become your sample. Okay. Now comes the stratified random sample. So proportionate and disproportionate. I think I have a slide for each of these, so I will run through the slides. So this is important. Every object will have an equal chance to be selected. Okay, and the objects are selected independently. So it is known as sample with replacement. So with replacement means now every object is not dependent on any other object. So every object will have an equal probability to be picked up. Okay, so for example, now I have this, let's suppose, population. Now I have to pick up few states from this. Okay, now see, every state has as a number assigned to that particular state. Now I will go with some kind of a random number generator. So random number generator is something like this, like like in during when we were kids. Okay, what we generally do. So we will have some kind of box in that we'll put some different chits, right? Every time we shuffle it and then we pick it up and we'll get some number. And that's how, we used to play, right? So here, if you say that I need 10 observations, so it will go and generate the numbers out of these 20 numbers randomly. So this is how it will generate the numbers 99437. So every number has a equal chance to be picked up. So this is how it has generated all the numbers. So if I have 20 is my population size, and if I say I want a sample of 4, so here wherever you see capital N, then that is known as population size. And small n is known as sample size. So here the capital N means the entire population. This is my entire data set. So I've just taken a small data set for you to understand. So I have 20. 20 is my entire population. Okay, and from that I need only 4 observations, which I will consider as a sample. So it's just like you close your eyes and pick any number out of 20 from 1 to 20, and that would be my sample. So it is as simple as that. Now comes the stratified random sampling. So here, population is divided into non-overlapping subpopulations. So now you have basically a population. Now you can create a strata, something like this, okay? So I want a clear representation of this population. So first I will identify the subpopulation inside this population, and from each of the groups, I will randomly pick samples. So my sample would be like this. Again, here would be these 4 stratas. And from each of these strata, and again, the randomly certain observations will be picked up. So in that case, now this sample will be the clear representation of this population. So random sample is selected from each stratum, potential for reducing the sampling error. So if you don't recognize these stratas or stratums, okay, in the population, uh, then you may miss out uh, certain groups, okay, or certain entities with certain characteristics, okay, and during your analysis, that particular minority group will not be represented, okay, so your analysis may go wrong. In terms of machine learning, if you haven't used any observation for learning, related to that minority group, then if you once the model is trained, if you want to predict anything related to that minority group, the model will fail. Okay, it will not be able to predict because while learning, you haven't provided those kind of scenarios. It's just like, if I don't uh, give you enough questions related to a particular topic to learn, and definitely when you go for the main exam, you may consider that as out of syllabus and you may not be able to attempt that particular kind of question. So if there are some kind of a key uh, or important statums available in your data, then you need to identify that. And from each of those strata, you have to find out you have to extract a sample out of that particular strata. So it will reduce your sampling error. Okay, if your sample is not good, then everything, okay, will go for a toss and everything will leads to an error, right? So that we call as sampling error. So at the first instance only, it is very important you are selecting the right sample. Now comes the proportionate. Now this is important point. The percentage of this sample taken from each stratum is proportionate to the percentage or that each stratum is within the population. So what does that mean? So for example, in the population, I have these 4 groups. Okay. Now let's suppose this particular group represent 10% of the entire population. Now this represent 30%. Okay. Now this represent 20% and this represent how much? 30, 50, 60. Let's suppose 40%. Okay. Now, if this is the case, now in the sample also, the representation should be in the same proportion. So then it is considered as a proportionate stratified random sampling. If you don't consider the proportions of the strata, then it is known as disproportionate. Okay, if it is different. So better would be to have a proportionate sampling. So in that case, whatever in the population you see, the same thing you see in a smaller scale in sample. Okay. So for example here, okay, so in the data, let's suppose I'm creating a group by age. So I have a 20 to 30 years old group, stratum 30 to 40 and 40 to 50. Now in each of this group, again, I will see that what is the proportion of the people in this particular uh, stratum. Okay, and then accordingly, I will go and generate the sample. So any questions on this? Is it clear? Simple random stratified sampling. Okay, now comes the systematic sampling, which is non-probabilistic. So here we go with our convenience. Okay, so you might have seen that again. In I always take this example. So during our childhood days, we generally do all these things. Okay, in sampling things. So if we have to distribute the chocolate, okay, we do it we go with a random sampling because we don't want to get biased. Okay, so because otherwise it may lead to a fight. Array, you got that chocolate, I got this chocolate, right? So then we say, okay, let's have a fair deal. Okay, I close my eyes and then I will distribute it. Okay, that's how. And when we play some cricket matches or something like that, gully cricket, okay, there also we do this kind of thing. Okay, now who will bat first, right? So we'll put some numbers. Okay, and then we ask them to choose. Again, it's a random sample. Sometimes we do a systematic sample. We say that, okay, everyone call some number, okay, 1, 2, 3, 4, 5, 6, and then uh, okay, after certain number, okay, whatever number comes, okay, then that will be picked up. That person will be in this particular team, something like that. Okay, so this systematic sampling is something like that, based on the convenience and based on how easy it is. We go with this systematic sampling. Okay, so population elements are an ordered sequence. So whatever elements are there in the population, they will be in some order. Okay, we will assign some number to that, and we will say that, okay, all the odd numbers. Okay, I'll just consider randomly. I'm just taking one example. I'll just say that whichever element has been assigned with an odd number, I'll consider that as a sample. Okay, or I will take first sample element from a first K population element. Okay, so that means I'll divide the entire data into K groups, and from there I'll pick one uh, sample from each of the population. So here I'm taking some systematic step. So probably it may happen that if I'm ordering it, so I may miss out certain extreme values, or I may miss out some smaller values, or whatever. Okay. So that may lead to some selection bias because I'm feeding some systematic way of picking up the observations. So in that way, it may lead to some kind of a sampling error. Again, in certain cases, uh, where it is highly difficult, to collect the entire data and, to do some kind of sampling on top of it. So we generally go with systematic sampling. We say that, okay, just take nearby places and just, if you have 20 places, just pick closest five villages or five places and do your survey. Usually people do, and that they do because of the convenience. Okay, and it would be relatively easy. But whatever analysis comes out of that sample may not be that accurate as we get, through random sampling. Okay, so for example, this is an example. So purchase orders for previous fiscal year are serialized from 1 to 10,000. So all the previous fiscal year purchase orders have been collected and ordered in a serially, and there are around 10,000 such orders. So the total size of the population, capital N, is equal to 10,000. Now I have to generate a sample of size of 50 and equal to 50 for auditing purpose. Now what I will do is I will divide the entire data into different subpopulation. So let's suppose 50. So there would be a 200 population with 50 size 50 each. Okay. And then what I will do is the first sample element randomly selected from the first 200 purchases. So one population will have 200. So like that, I will have 50 samples. And from each of the sample, I'll just take the first element. And that's how I'll get a sample of size 50. So now this could be a systematic sampling technique. Okay, here I've used this particular technique. Okay, this method, to generate generate the sample. So if you're using any mathematical way or some kind of logical way to create a sample, that comes under systematic sampling. This is just an example. Now comes the cluster sampling. Now what happens in the cluster sampling is sometimes you will find different kinds of characteristics and you will get puzzled or you will get confused, right? How many stratum should I go ahead with, right? So you will have age, you will have income, you will have region, you will have race, caste, everything, okay, occupation. So you will get confused like what characteristics or what kind of stratum should I take, to generate my sample. So to do that, you can go with some kind of a clustering techniques. So in machine learning, we will discuss about clustering technique where you can pass multiple characteristics of the observations of the data, and it will, based on the patterns, it will come up with different kinds of clusters. Cluster is nothing but again, it's a group. Okay, and based and from each of those groups, again, you can identify the proportion, what is the proportion of each of the groups, and then you can generate the sample from each of those groups. Now that is known as cluster sampling. So where we have to first uh, identify the clusters, unique clusters in the data through again certain algorithm, and then we can consider that as stratas, and then based on the strata, we can generate the samples from each of the strata. Okay. So advantage, more convenient for geographically dispersed population. As I mentioned, if there are multiple characteristics, okay, and which is hard for you to define or identify, then you can go with this kind of clustering technique. Okay. So I think rest of the points are self-explanatory. So I'll jump to this now, non-random sampling. Now, I think most of the time, probably whoever has done any kind of survey analysis, okay, in the past, usually we go with these kind of sampling techniques. So when I was doing MBA, we have to do a lot of primary research. So for that, we need to do a lot of surveys. So generally, we go with this kind of sampling. So we used to distribute all those survey templates or pamphlets, to our nearby people. Okay. So we used to give to our friends and say that, okay, get it filled by your relatives or by your friends or neighbors. Okay. And get it tomorrow. So this is all convenience sampling. Okay. Where you select the sample elements. Okay. Based on your convenience. So like your friends, your relatives, your neighbors. Okay. So that comes under convenience sampling. Or even when you are, even for machine learning analysis, let's suppose you have the access to one Excel file, okay, and then you will use it because you have the access to it. So you don't bother, to collect more data and get access to other data sets and then generating a sample out of those. So that is known as convenience sampling. So if you have short of time and you want to do a quick analysis, then we can go with this convenience sampling. Then comes the judgment sampling. So now if you are selecting the elements based on your judgment, okay, so everyone will have a different way of thinking. Everyone will have a different thought process. So if you are using some thought, okay, or some logical way of picking up the elements, then it comes under judgment sampling. If your judgment goes wrong, then your sampling goes wrong, okay, and you will get a incorrect sample, okay, which will not represent your population. So again, it may lead to some kind of sampling error. Then the quota sampling. So here, it's based on the quota. Okay, you will say that, okay, from this group I will just take 10%. From this group, just you only fix the quota. Again, people will fix the quota, and then based on that quota, you generate the samples. So that is known as quota sampling. And then comes the snowball sampling. So this is the technique, okay, we generally we use, okay, when it comes to primary research. So it is like telemarketing or something like that, you have seen, right? So you give information to three people and then ask them, to forward it to another three, right? So it is known as snowball. It is like rolling. Okay, your survey is kind of getting rolled from people to people, people to people, and that's how you will. So even on the digital side, when you do this kind of pass this kind of surveys, then this is how it will get passed on through multiple other people. So this is known as snowball sampling. So again, it can be biased because see, So for example, now you have shared this sample to your friends. They will also may share to their friends. So you may target to only one particular age group. Okay, so more number of observations would be confined to a particular age group as of your friends. Okay, so in that case also, it may lead to some kind of a biasness. So you have to make sure you know where exactly you have to go with a random sampling and non-random sampling. If you have to do some kind of a statistical analysis, some kind of a machine learning and a kind of model development, then it's always better you know to go with a random sampling rather than non-random sampling. But if you are finding out some kind of a market pulse, you know what people are buying, how they what they want to see, then this non-random sampling could be you know applied. But for statistical analysis, always better to use random sampling. Now comes the error. So, so as I mentioned, the non-random samples are not appropriate for analysis using inferential statistical methods. Okay, sampling error occurs when the sample is not representative of the population. Okay, and we have seen that how what are the different ways by which you know you can uh, generate the sample which can represent or which will represent the population. Okay, so some of the errors which you may see is that in the original data also there could be a missing data. Even the recording could be incorrect. The data entries could be incorrect. There could be some kind of analysis errors. So what will happen is even when you are generating the sample, okay, the values may not be correct. Okay, then that becomes a non-sampling error. It is not a sampling problem. It is a data problem. So there could be two problems. Okay, when you are making the analysis, one is probably your sampling technique may not be correct because of which you are leading to an incorrect analysis. Second thing, your data itself is not correct. Okay, there's a lot of discrepancy in the data. Let's suppose you have used a right stratified proportionate sampling technique, okay, to generate the sample, and you have clearly and very nicely you have selected all the observations, which is clearly representing your population. But what if, you know, if the values are incorrect in those observations? If they are missing data, if there is a data entry problem, okay, if there is some kind of people who have done some analysis and uh, captured certain values in the data are incorrect. Okay, so that may also lead to an error. So now we have to, as a data scientist, we need to make sure that how to minimize this error. So we have to go and treat the data to improve the quality, and at the same time we will use a right sampling technique to generate the samples. So for example, in the market survey, okay, when people say that uh, I don't know, okay, I cannot say or put something else in the answer, okay, overstate in their answers. So generally we see that, okay, when you fill the survey and you don't have time, you just put anything junk, okay, or non-relevant things in the fields. Okay. So so now because of that, your data become uh, incorrect, and and that may lead to a lot of errors. Okay, so this is our errors are sampling errors and the non-sampling errors. Okay, and guys, stop me wherever you have any questions. Okay. Now this is the whole process of inferential analytics. Okay, so what happens is so now you have this population. Okay, and this is, let's suppose this is the parameter about which we have to derive the inference. So what you will do is, as the collecting the data for entire population is not easy, and even if it is there, analyzing or processing that data could be costly and could be time consuming. So what I will generally we do, we go and select a random sample, and on that random sample we go and measure that particular statistics. Okay, so now we are denoting it as X bar. Now, based on that X bar, we will kind of estimate this population parameter. And based on this X bar only, we will infer something about this population parameter. Now, this is known as inferential analytics or inferential statistics. This is the whole process. Now, if your sample goes wrong, if there is a sampling error, then this would not be accurate. Okay. And whatever inference you will derive based on this about the population parameter will go wrong. So that's the reason the sample is very, very important. Okay. While you are considering the sample, you have to make sure that you are selecting the right sample. So making statements about population by examining the sample result is known as inferential statistics. So these sample statistics, these are known because you have the sample. You know what observations are there in the sample. So you know all the characteristics of that every object in the sample, right? So this is known. So based on this known data, you go and calculate these sample statistics. So sample statistics, as I mentioned, these are X bar, variance, standard deviation, and the proportion. Okay, so these are known as sample statistics. Once you calculate the sample statistics on sample, on top of this, you will infer something about the population parameter, which is unknown. So as I mentioned, this data science is all about knowing something about unknowns, right? So when you're going with machine learning, so you're predicting. What you're predicting? You're predicting certain unknowns, which is not easily can be estimated, right? So you take the historical data based on that patterns, based on the learning, based on the knowledge of those past historical events, you can able to predict something about the unknown. So here also, if we have to comment something about the population, it is hard because that is unknown to you. If I ask you how much typically a person, um, what do you say, a person walks, okay, in a particular day, okay, of age group like between 40 to 50, how many steps or how many kilometers they walk, it is unknown to you. It is very hard. Okay. What how would you analyze that? So you will first go and sample. So because it is not possible for you to go and check with every person of that particular age group, and connect with them and ask them, how much they walk, right? It is very difficult. It's very hard, impossible. So what you will do, you will go and take the sample. So generally we do the convenience sampling only. We'll ask the people who are around us and whom we know. And once we get the sample, we will go and find out the sample statistics. So some few people may say that 2 kilometers, 3 kilometers, 4 kilometers. Few people may say that, okay, I don't even walk, okay, in a day, every day. So like that, you will get a entire data and then you will calculate the mean. So on an average, let's suppose it is coming as 1.5 kilometers. Now, with that sample statistics, you have to infer about the population. Now you have to say that, okay, generally people in that particular age group, 40 to 50, they walk for around 1.5 kilometers. Now, that is known as inferential statistics, where you are making the statements about the population based on the sample statistics. So I'll take a pause. Any questions?
Sir, is there any limitation on how to check the sample size, or is it up to us?
Sorry, can you repeat the question again, please?
I was saying that is there any limitation on the sample size selection, or
Yeah.
it is only up to us?
See, again, the sample size depends on multiple factors. One is like what is the kind of analysis you want to do, depending on the use case and the problem statement. You have to decide the sample. When it comes to machine learning problem, your sample size may change based on the model accuracy. So let's suppose you have picked up 50 observations and then you have fed it to the algorithm. Then algorithm enable and you are getting the accuracy let's suppose of only 75%. Now what you can do is you increase the size of the sample, because there could be a chance that that sample which you have considered earlier is not capturing all the different scenarios. Then you increase the size from 50 to 100. Now you pass it to the algorithm. Now probably, if your accuracy improved from 75% to 85%, that means, okay, now uh, the sample size is important factor, which is improving your model accuracy. Then you keep on increasing the sample and then see that, okay, till what extent you can improve the accuracy. So it is a subjective, and depending on the use case, like what is how complex the use case is, accordingly you have to decide the sample size. For example, the population, India population, let's suppose. If you are taking the sample, if you go with the 10 uh, observations, can you able to represent the entire population? No, right? So you have more than 20, what do you say, states. So just 10 observations would not be enough, right? So you have to decide on the right amount of sample which can clearly represent the population. So depending on the use case, depending on the problem statement, depending what kind of analysis you want to do, you have to decide on the sample. So there is no thumb rule, there is no one answer or any fixed sample size.
Okay, sir.
Okay.
Okay.
Any other questions? Okay. So now in inferential statistics, there are two things which comes. Okay. Uh, One is like we just estimate the sample statistics. Okay, and based on the sample statistics, so whatever measures of central tendency and measures of dispersion, like mean, variance, standard deviation, we call it as an estimation. So we estimate those sample statistics, and based on that, we make a decision about the population. The second way of inferential statistics is using hypothesis testing. Now, let's suppose we have a sample, and based on the sample, we have to prove something. Okay, so there would be some kind of hypothesis defined, and we have to test whether those hypotheses are correct or wrong. So for testing purpose, okay, we take the sample, and based on whatever evidence we get from the sample, we make the uh, we choose the hypothesis, and based on that hypothesis, we can make a decision about the population. For example, my hypothesis is, so there are basically two types of hypothesis, which we will discuss again in detail. One is like null hypothesis, second is alternate hypothesis. Let's suppose null hypothesis says that this particular drug is effective. Alternate hypothesis would be just opposite to that. It will say that this drug is not effective. These are the only two scenarios which may come, right? There wouldn't be any other scenario apart from this. Either the drug would be effective or the drug would not be effective. And now for the, I would say, for the companies to decide whether to launch this drug or not depends on either of these two hypotheses. If it is effective, then they will go and they will launch the drug. Otherwise, they will not. Now, how that testing can be done? So definitely testing on every drug, okay, or every pill, it is highly impossible, right? Okay, or every sachet or every bottle of that drug, going and testing is not possible, and it is not recommended also. So you will waste all the drugs. So what you will do is you'll take some sample, okay, and on that sample you will do the experiment. So whatever experiment result comes, okay, on that particular sample would be your sample data, and on that you will do the analysis. So on that you go and use this sample statistics, find out, calculate the mean. Mean means like how much, let's suppose it is related to blood pressure. How much effective the drug was on each of the objects or each of the person, people in the sample. And then you note it down. So here it is 10%, here it is 20%, here it is 5%, 6%, 7%, right? Whatever it is. Okay, now you take the average. That would be your sample mean. So for example, on an average, by using this particular medicine, there is a control in BP by 7%. Okay. Now, can you make this statement for the entire population? Can you just say that, okay, this particular drug is capable of reducing the BP by 7%? So now here comes again the confidence. On what level of confidence can you make that statement about the population? So all that comes under hypothesis testing. Okay. So where we make certain experiments, we conduct those experiments, and then based on the experiment results, we take the conclusion and we decide about the population. Okay. This is something we will cover during probability. So I'm skipping this. I'm just seeing if we have any example. All these things distribution we will cover in the class later. Okay, so here there is an important concept known as central limit theorem. Again, it's a theorem. Okay, so it's all about distribution, guys. So we have discussed about the normal distribution. It is a very, I would say, very important distribution when it comes to probability distributions. And the name, why they have named it as a normal distribution is, in the universe, there is a tendency that if you collect the data related to any scenario, okay, if you're collecting the data which is continuous, so you, for any state, if you go and collect the data, generally it will, for the population, so it will generally follow the normal distribution. It is very normal, okay, and it is a universal truth kind of thing. That's the reason they named it as a normal distribution. So as we say that in the universe, whatever data you capture which is continuous, okay, for the population, it will follow the normal distribution. That means it would be symmetric, okay, it would follow that bell-shaped curve, okay, distribution. So if you are generating a sample, in the statistics, we assume that even the data in the sample is following a normal distribution. Okay. Now, if the data in the sample is not normally distributed, so the biggest assumption what we make is, so let's suppose this is a population and we generate multiple samples. This is another technique. Instead of going with one sample, I will generate multiple samples. Okay. So random sampling, it's easy for me, right? I'll pick 50, then again I'll pick 50 every time, different 50 observations may come, right? It's highly impossible that I may get exact same 50 observations more than once, right? So I'll get different combinations of observations in my sample. So if I go and find out the sample means for each of the samples, what this central limit theorem states is the distribution of these sample means will follow a normal distribution. Are you getting what I'm saying? The means of the sample will follow a normal distribution. The another way of putting it is because in the statistics, we generally assume that the data has to be normally distributed, because whatever theorems and whatever techniques which are there in the statistics, it will work well if your data is normally distributed. And why it will work good is because your data is not biased. If there are any outliers or extreme values, definitely your data is biased, and all the analysis will get biased, right? So in that case, it's always better, to check your data whether it is normally distributed or not before the analysis. So what central limit theorem says that, okay, if you have one sample and if it is not normally distributed, do one thing, you generate multiple samples, okay, and consider the means of every sample and if you go and find out the distribution of those sample means, it will follow the normal distribution. Now you can perform the analysis on top of this. Or else what you can do is you combine all these samples together and create one large sample. And if the size of the sample increases, then also there is a high chance that your data will distribute normally. Okay, will be normally distributed. So here says the sample means from the population will be approximately normal as long as the sample size is large enough. Okay, it's just the theorem, guys. Okay, so based on this theorem, we can think of how to deal with this normalization. Okay, so again, I'm talking about the concepts. So when we discuss about the use case, we will see that, okay, how we can apply these theorems. So this theorem says that if your data is skewed, so you're taking the sample, there could be a chance, right? You in your sample, you may select a extreme value, right? So because it's all randomly picked up observations, right? So you are not using any kind of logic in selecting the observations. So while selecting randomly, there could be a chance that you may select the extreme values, and because of which your data may not may get skewed. Okay, it may not look like normally distributed. So in that scenarios, what you can do is you take multiple samples and you calculate the mean of each of the samples. And then once you analyze that means of the sample means, then it will follow a normal distribution. Or else you increase the size of the sample. If you increase the size of the sample, generally your data will become approximately normal. So that is what is known as central limit theorem. Okay, even if your population, whatever data you have, okay, in your database, if that is also not following normal, but when you're generating a sample, it will show you normal. Okay, so this is your sample, right, of size n. So see, in this sample, let's suppose you have chose few extreme values on the right, and because of which this distribution looks skewed, okay, positively skewed. But if you start increasing the sample size, it will get, it will convert to a normally distributed. So what will happen is, as in this sample, there could be one or two observations which are extremely high. But when you keep increasing the size of the sample, there could be a chance that more number of observations may get selected, okay, which probably were looking as extreme values earlier, but later, it is kind of fit into the distribution and your data may look like a normal curve. Okay, and that is known as central limit theorem. Okay, so is this clear, central limit theorem? And this I will again and again I will cover. So because you need to understand all the distributions. So once we talk about the probability distribution, then you will get even more understanding about what we mean by this distribution, okay, data distribution. So in that data distribution, one very popular distribution is normal distribution. And all the statistical analysis, whatever we do by assuming that the data is normally distributed. If your data is skewed in the sample through this central limit theorem, we generally consider that if we consider more samples, my data will get normal. Okay, or else if we increase the size of the sample, it gets normal. So that theorem is known as central limit theorem. Any questions? Are we good? So more of this, will get clarified once we discuss about the certain use cases or examples. But I'm just quickly covering the concepts and then we will get into the examples. Okay. Now here, yeah. Now we talked about estimations, right? In inferential statistics, there are two types. One is estimation, second is hypothesis testing. So let's talk about estimates. So we generate the sample from the population and then we calculate the sample statistics, which we call as estimates, okay, or we can call it as point estimate, okay. Now, let's suppose the same example we will take, okay. I asked you to find out how many kilometers in a day typically a person walks, okay, in the age group 40 to 50, okay, how many steps or how many kilometers. And let's suppose you have come up with a number like 1.5 kilometers on an average. Now I'll say, how confident are you? Or how how much accurate this number is? Okay, you will have no answer. Okay. Now through statistics, we can bring that confidence. Okay. Now you tell me, let's suppose there's one answer like point estimate. You're saying 1.5 kilometer. Would you be more confident on that particular answer? Or if I allow you to give me a range, okay, for example, you may say that, okay, somewhere between 1 kilometer to 4 kilometers. I will allow you to give you a range. So which one would you choose? Where you will have more confidence? On point estimate or on a range? Guys,
Range.
of course, range, right? So now through this statistics, we can come up with that range, and the range will be assigned to the confidence. Now again, second question. Let's suppose there are two answers which I can allow you to give, and that two could be a range. So one range is, let's suppose 1 kilometer to 4 kilometers. Another range is like 0.5 kilometers to 7 kilometers. Which one you choose with more confidence? The larger range or smaller range?
Larger range.
Larger range. Because there is a high chance that, okay, your population parameter, which is actual mu, okay, of the population will lie in that particular range, right? So as I'll make that range narrower, your confidence will go down. Okay. As I increase the range, your confidence would increase, because it's highly possible. Okay, there is a very rare chance that, okay, somebody may walk, more than 7 kilometers, okay, and even less than 0.5 kilometer. So definitely you will be more confident that, okay, my actual value would fall in this particular range if the range is wide enough. So now this range, so now here you are using just your intuition, to come up with that kind of range. But now in statistics, we will learn that what is the scientific method of coming up with that particular range. I'll take a business scenario. Now, if based on the data, if I go and tell to my business that uh, your sales estimate is $200 per day, okay, that's what I'm seeing in the historical data. Now, business has to plan based on that. Okay, so it is $2,000 per day. Okay, fine. Okay, or so based on that, he will plan the resources, plan the material and everything, right? Now, what if it goes wrong? So he will come and he will scold me, right? Saying that you said $2,000 per day, but I'm seeing that it's only 1,000, or I'm seeing it's coming 3,000. So I'm unable to do my business properly. Okay. So I may say that, okay, you asked just one number, I gave you the point estimate, and this I've generated, calculated through sample. Probably I haven't selected the right sample. And definitely whatever sample statistics you will generate, there would be a very rare chance that it will accurately match to your population parameter. How whatever, perfect way, you come up with the sample, but there would be some deviation. Now, those deviations you can avoid by considering the interval. Okay, in that's where you can minimize the risk. Now I can go to the business and I'll say that your per day sales could be somewhere between $500 to $2,000. So here I'm minimizing my risk, okay, of getting inaccurate. Okay, so now the business may, most of the times, it may see that their sales are falling in that particular range. 90% of the times, the sales are falling in that particular range. So in that way, it would be more accurate to come up with an interval rather than going with an estimate. So when we are defining, when we are going with statistics, we cannot 100% accurately, we can say that your this is the population parameter, okay, by using the sample statistics. Definitely, there would be little bit of deviation. That deviation you can control by using this interval. Now, this interval, we call it as confidence interval. Okay, so here the point estimate is one single number, which is your sample statistics, and which may go wrong. So for that reason, we go with the confidence intervals. It provides additional information about the variability. So most of the time in our real scenario, in our real life, we generally go with a range. We say that how much time would you take? You will say that roughly between half an hour to 1 hour. Okay. So whenever we want to safeguard ourselves, right? So we will, instead of giving a point estimate, we'll give a range. So in statistics also, we can come up with that range or that interval by certain method, which is scientifically proven method. And based on that, we can come up with this width of this confidence interval. Okay. Let me show you how we calculate this confidence interval. So for example, this is just a pictorial representation. Now I have a population. The population mean is mu, which is unknown to me. Then I have derived the sample out of that population and then calculate the sample statistics. I'm seeing, and now it has come as 50. Now, based on this sample statistics, I will define the confidence interval. So confidence interval will be uh, will be will be proportional to the confidence level. Okay. So if your confidence level is 95%, you will get certain interval. If it is 90%, then you will get certain kind of interval. So your interval width will be depend on the confidence level. So in statistics, we can say that I'm 95% confidence that this mu, which is your population parameter, will lie between this 40 and 60. That confidence interval is derived based on the sample statistics. How it is derived is uh, through this formula, which says that this is the point estimate, which is coming from your sample statistics. Let's suppose this is X bar plus minus this entire term. Okay, this entire term is called as margin of error.
Shrikant, are you sharing something? I mean, we are only
It's not.
seeing the PowerPoint.
Oh man. Now can you see it?
Yeah, now we can see the confidence.
Oh shit. So okay, so I'll repeat again. Sorry guys, have told me. Can you see this point estimate slide? Yes.
Yes.
Okay. Okay. So I'll repeat again. So as I mentioned, when you are going with a point estimate and you want to infer about the population, you may go wrong sometimes. It cannot be 100% accurate because you're taking the sample. So there would be definitely some amount of sampling error. Okay, because of which you cannot accurately say that okay, this is what is your population parameter. Okay, so this is the average income of certain kind of people or group. You cannot 100% say that. So in statistics, to avoid that kind of risk, okay, we generally go with an interval, because when we go with an interval, our confidence of stating or inferring about the population may go high. Okay, so for that, what we do is we take this point estimate and we do some kind of a plus minus to this particular estimate. So we say that, right? How much is the risk? You say that, okay, 10%, but plus minus 5%. Okay, so it may range somewhere from 5% to 15%. We'll give a range. Okay, so somebody, like, when we estimate something, we estimate, or we say that, your cost may come up till 50,000. So if you go and ask again, are you sure? Are you sure? Then they will say that, okay, because when you say are sure, and that means you are checking with them then how accurate that person is, on that particular cost. If he's not completely 100% confident, then he will say plus minus 10,000 here and there, right? We generally talk in those language. So here in statistics also is the same. So here we are inferring about the population parameter based on the sample statistics to add the confidence to this particular inference. We go with a confidence level. With the help of confidence level, we can be more confident while inferring about the population. So this point estimate plus minus certain term. So that something you can see in this particular formula. Okay, it's point estimate plus minus this particular term. This we called as margin of error, MOE. So it is point estimate plus minus MOE is equal to confidence interval. Okay, now I mentioned this interval. If you increase the size of this interval or the width of this interval, your confidence level increases, right? You only agreed on that. Now, how can we bring that particular thing into this particular equation? We will see. Now here we have these two measures, which is reliability factor and the standard error. The product of these two terms, two measures, is known as margin of error. Now we will understand how we can bring that confidence level into this mix, to define the width of the interval. Okay, so in this picture, which you just missed out, here this guy, he's saying that based on the sample statistics, which is coming out to be 50, with the help of confidence level, he is coming up with this interval. He's saying that I'm 95% confident that your parameter, population parameter mu, will fall between 40 and 60. So that means 95% of the time, this the values will fall between 40 and 60. So for example, I'm calculating the quality of my product. So I'm saying my quality of the product will lie between 40 to 60. So every time, whenever I'm measuring the product quality, it is 95% times it would fall in this particular range. So that means I'm 95% accurate. Now you would be thinking, why can't we go with 100% confidence? If we go with 100% confidence, this interval will not make any sense. Sometimes it may show you as minus infinity to plus infinity. If you give such a wide interval to anybody, it will be of no value, right? If I say that how many kilometers a person walks, if you say that from 0 kilometer to 50 kilometers, so I've given a very wide range, and definitely 100%, there is a I don't think there is any possibility that anyone will walk more than 100 kilometers in a day, right? And even so, 0 and 100 kilometers is a very safe interval for me, and 100% it will be accurate. But does it make any sense for making me to make any decision? Probably not. So as the interval, if it's narrow, if it is short, then only it make more sense. Then only you can take a concise and better decisions. Okay, so tomorrow we will discuss about what is this reliability factor, what is this standard error. So it is a mathematical equation formula. That's something we will understand, and how it is tied up to this confidence level, we will understand. There comes a probability. So you have to be little patient, guys, because these are all new terms, and core mathematics, and you will find here. So anywhere, if you have any confusion, you have to ask me, okay? And then only you will get these concepts, okay? But tell me now, whatever we discussed so far, is it clear to everyone? At least
Yes,
on the
sir.
concept level, why point estimate, why confidence interval? And every time, guys, whenever we are learning this concept, you have to relate it to your real life. In real life, we are doing this, and all this data science is derived out of our real life. How we as humans, we make decisions, we infer about something. And now this is more of a scientific way. We do it intuitively. We do it through our gut feeling, through our experience, right? And now here we will see that how this can be done through a scientific way. Because over the period of time, what we have observed is when people are making the decision based on their gut feeling and based on their experience, probably because of certain limitation, we cannot remember everything, we cannot look out from various dimensions, our decisions may go wrong. If you look at the data, these are like mathematical and scientific way of doing it. So there's less chance of making any error. Okay, so if the data is correct, so it will speak out, um, whatever data has, okay, information. So it will speak out in that particular way. So that's the reason people have seen that when they are making their decisions based on the data and based on the output of the data, then those decisions are more effective and they are more accurate. Okay, so we call as a data-driven decisions. And we have discussed in the past, right? What are the different kinds of decisions which any typical business would make, okay, and how this data science can support that decision-making process. Okay, so cool. So is all clear, guys? No questions? Okay. So if no questions, then tomorrow I'll ask questions. Okay. So go through this recording, hear it once again, and I'll go a little slow. I'm going very slow, guys. So I'm going uh, covering every topic in more detail so that slowly you get that feel. And there will be a lot of parallel topics, guys. As I have just covered normal distribution. If I don't cover normal distribution now, this concept would not be clear. If I go and cover that normal distribution now, then even that concept will not get clear, without covering this topic. So there would be little bit of overlap of these topics. Uh, so if normal distribution is not clear, then park it for some time, and that will be get cleared when we will discuss about distributions. Okay. So just think about it that it is one kind of distribution, which is very important to assume when we do the statistical analysis. And if any data is not following that normal distribution, then there is a theorem which is defined as central limit theorem, which says that you go and generate multiple samples, and once you calculate the means of every sample and then check the distribution, it will come as a normal distribution. Or else you increase the size of the sample, then it will uh, uh, convert into a normal distribution. So that's a theorem which we will apply when we are working on certain kind of use cases. All right, so I'll stop it here. Okay, so we'll connect tomorrow. And Thursday, guys, I'll give you certain exercises tomorrow, and I will expect you guys, to work on it during the weekend, Saturday and Sunday, and then on Monday we will discuss on those questions, because these are the very important concepts, and I have to check whether you are getting that concepts or these concepts clearly or not. If you don't get these concepts, it would be difficult for you to understand other topics. Okay, so please go through whatever we have discussed so far, and tomorrow after the class, I'll give you certain exercises to do. Okay. All right, guys, then thank you. We'll connect tomorrow. Have a nice day. Take care. Bye-bye.